Hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal? I hope you guys are doing good. In this, we're going to see problem minimum time to visit all cells in a grid. It simply says that you are given a m cross n grid, as you can see, with which consists of non-negative integers. All integers are either 0 or positive, where grid row column represents minimum time required to be able to visit the cell row comma column. Considering we are moving on to cells and each move requires 1 unit of time, thus any value on a cell represents that to reach here he should have traveled 4 units, and after traveling 4 units or more, when he comes to me his time should be more than or equal to 5, right? When he will come to me after that, okay, let's say he landed here. As he landed here, after that his time should be more than equal to 5, only then he can land at me. That is what this value even represents, right? This is exactly what they're saying, that which means you can visit the cell row comma column only when the time you visit it is greater than or equal to the actual grid value. Ultimately you are standing in the top left cell, which is 0 comma 0, and because you are starting from here you don't have elapsed any time whatsoever, thus it needs to be 0, and they're also mentioning that it will be 0. So there's at in the 0th second, and you must move to any adjacent cells in the 4 directions. Now the movement is nothing but the 4 directions which we have. Obviously, the moment they mentioned 4 directions we can move off, it starts giving us the vibes of graph traversal, which, because okay, starting node is 0 comma 0, ending node will be m minus 1 comma n minus 1, and we have to just ultimately reach there. That's what it feels like. And each move you must take 1 second, so each move require 1 second. So how we should travel? Okay, we can travel here, obviously we can, because when I do one move I will be able to reach here. The time here so far is 1 second. Again, can I travel here? No, because if I travel here the time will be 2 seconds, and the current requirement is 3 or more. I cannot move here. So is it that I can never move here? No, I can move. How? I will go back, t will become 2. Now I'll come back again, t will become 3, then I go back, t will become 4. Now t is more than or equal to my 3. So you see that I was still able to reach here. It's just that I have to keep on going back, coming forward, going back, coming forward. This is the actual way to increase my time. To increase my time. How you actually waste time? This is wasting your time, which you will have to do, because this is the requirement of the problem. Now ultimately we have to return the minimum time required in which you can visit the bottom right corner. Now when they are mentioning minimum time, the first thing which could have come to your mind is, Aryan, I know that I have some possible time range. That okay, let's say minimum time, again imagine minimum time could be 1, or let's say 1e9. Again, I'm just giving some arbitrary numbers. Then I will simply apply a binary search, and at a specific time, let's say t mid, I will just be able to figure out, is it possible to reach from start to end with this specific time? Okay, and then if it is possible, then I will try to go to the left. This is what you could think of, because of minimum time using a graph. This is the first thing which also came to my mind. Then the moment you will go on to, okay, is it possible for you to reach your destination with this possible t mid? You will say, okay, we will start from here, then I have to go to some specific cell. Obviously, I will choose greedily to go to a cell having the lesser time, right? Okay, I reached here. Then again, my t has become 1. Now, as I move on to next cell, okay, as I move on next cell, t equal to 2 will become, right? Why I should not go right now at this cell? Because obviously to go to this cell I will have to increase my t. Again, you might say, Aryan, but you have this fixed number of t mid, right, which you have to check out. See, this t mid ultimately indicates if it reaches the end, which is if it reaches the final destination, what is that t value ultimately it could be giving you. It doesn't mention anything about intermediary t's which could be there. So To check even this is possible or not, I am still going greedily to the minimum. Whoever have the minimum time, that as in like whoever has the minimum value of the cell, I will try to go there itself. Okay, so at t equal to I am here. Now to reach next cell, okay, I will again greedily I chose the cell which is having lesser value. At t equal to 3 I reached here. Now t equal to 3 I am here. I have to go to the next cell. Next cell, anywhere I go, even if I go up, it will be t equal to 4. Okay, I go right, it will be equal to t equal to 5. I go down, it will be t equal to 8. Like there's a requirement of it. So you might say, Aryan, isn't it beneficial that you should go up? I'll say, okay, technically I can go anywhere. I can go here also, and here also, like not here, but yeah, any four directions I can go. Now you might say, Aryan, how will you go at 5? See, my t is 3. I'll go back, t will become 4. I'll come back, t will become 5. I'll come back, t will become 6. T became 6. Now you might say, Aryan, why didn't you not go up? Okay, go up. So what will happen? Simply, you go up, t will become 4. You go right, t will become 5. You come down, t will become 6. Again, t will be 6 itself. Now the question here is that what is the best possible scenario? What is the best possible scenario for you? Obviously, in this case, it would be much better if I would have started off and went on to t equal to 3, because again my ultimate maqsad is to reach to the final destination, and also parallelly I am trying to make sure that I am choosing the minimum time requirement cells. So here I choose the minimum time requirement cell which I had, which was t equal to 3. Again, this also was having that requirement, so we should be still good to try out this cell also. But let's say, okay, let's come back. So I tried this cell, which is this cell. My t became 4. Then I will try, okay, next cells. Okay, I will go on to simple my corresponding next cells. His requirement will be t equals to 5. What I'm trying to mention here is that what is my current cell value which I have, and how much time it will be needed to reach to the next cell, that will define his actual time. Which means that for this specific cell, as a cell, to know which neighbor to choose to go, these are its corresponding neighbors. I will say that to reach at this cell, the time required will be 6. How we figured it out? Simply from 2, if you want to go to, sorry, from t equal to 3, if you want to go to a cell whose value is 5, simply check it like this. Okay, you had a cell, let's say for t was 2. To go to a value which is, let's say, higher, you will actually keep on going back and forth. So I'll go back, became 3, come 4, again still it's less. Even if I had to go, I would have gone there, it would have been 5. I want 6. I'll still go back, I'll come back again 6. Now if I go back to the next cell, which is this cell, I will be t equal to 7, which is good. So how many shuffles you did? Or my question is that how much time it ultimately took before going there. Let's see if the value would have been 3 and I have to reach to 6. I'll simply go back, make a 4, come back, make a 5. Now if I go to there, it will be a 6. So you realized either the time to reach here will be the current time plus 1, which is, as you can see, current time was 6, or current requirement was 6 and the current time is 7, or it will be exactly as the current requirement, which is 6 itself. How? If the difference between these two is odd, the destination time will be the current time, the right? If the difference is even, then the destination time will be current time plus 1. So I can just have this kind of a modularity. So if I come on back from this cell, I want to choose greedily which is the best option for me to go to. But for that, I will know, okay, the difference is odd. The difference is odd. In that case, when the difference is odd, it is always possible to actually reach on to, again, sorry, the difference is even. 5 minus 3. When I say difference, I'm referring that time. So the time to reach here was 3. and I am at 5. So difference is even 2. So if I want to reach here, it will require t equal to 6 as time. If I want to reach here, it is just the next cell. It is just the next cell. Don't take the difference here. If you go on to the next cell, if it can become that value which is more than equal to, so no worries. So t plus 1, if it is more than equal to the grid value, you are good. So for him, the time requirement will be a 4. Will be a 4. So now you have an option. Choose which one, t equal to 4 or t equal to 6. Obviously, you will try to go towards a cell which is having a lesser t, right? Because ultimately you are going greedy and you want to get your answer done in as minimum time as possible. And here in this case, when you were doing a binary search, you were checking, okay, is it possible to ultimately reach end with the specific t? And ultimately, again, going greedily, you can simply traverse and apply your thing which you are doing greedily here. Now obviously choosing the minimum time place to jump onto and ultimately reach the end. Do you think in this entire approach, will it even matter if I use this or not? Like I'm ultimately going greedily. My teammate is never helping me until and unless I reach my end. As I reach my end node and whatever time was taken, like that specific time was the minimum time. And if that minimum time is less than equal to teammate, then I will try for lesser time. But again, in the lesser time approach, in my binary search, I will still be applying the same algorithm. Every time I will be trading the same thing, which means that this binary search is redundant, right? And you are still going greedily. That greedy approach is itself correct. What is this greedy approach? Before we go on to, let's see one more example. In this case, you start from here. You go on to the cell. You will incur a time of 1. But it was mentioned that the required time should be less than equal to your current time which you go on to. It is 2. The biggest issue is you cannot do any back and forth because you are just starting from the first cell. Thus, you cannot even move here or here. Answer is -1. So, the only possible case when the answer will be -1 is when your grid of 0, 1 or and the grid of 1, 0, if both are more than 1, in that case you will never be able to even get out of your grid and thus will never be able to reach your end. In every other case, you will always be able to reach your end because if you are able to jump on to the next node, then you can do any number of back and forth, back and forth, back and forth to increase your time. And as you can see, the time value is nothing but 1e5. So I can do a back and forth 1e5 number of times to even get higher number of values. So in that case, it is always possible. Then we just go greedily. When I say greedily, simply at every point, go and check that which neighbor to go on to and to know which neighbor to go on to. Again, obviously from the cell 0, I cannot even go here. I cannot even do back and forth. In that case, I will simply go on to this specific cell. I will simply go on to this specific cell. Okay. As I go into the specific cell, again I will try to see, okay, can I go here, here, here? And again, you might say, Aryan, can I go back? No, obviously you should not go back. Obviously will increase your time. When I say go back, I am referring that to reach here, obviously I might be needing to go back, but that I will take in consideration when I'm putting up time for him. So for him to reach here, if let's say the t is 1, it is 3, the difference is actually even. In that specific case, I know that the time he will need to reach here will be 4. As you can see, it is 1, so I'll go 2, 3 and then 4. And the same way to reach here, it will be nothing but t plus 1, which is 2. So the possible values, like the possible things which I can take, or the possible time will be nothing but either, again, if the difference is even, then have a 1 as a flag, or it has the flag is 0. So to reach at a specific cell, either that new cell, new row, new column, if it is either, it will be +1, I should say plus flag, or it will be nothing but that specific time value +1, time +1. Out of these two values, I will have to choose a value whichever I would be needing. And again, depending upon that, wherever I am going. Cool. And again, greedily choosing the minimum one. How will you choose minimum one? Simply you can use a priority queue in this case. Let's see the code. Exactly same as what I told, and also I will keep on telling you okay, what's happening at every point also. But again, this is exactly same as what we did at dry run while we were checking out. First, very base case, that if it is more than one, both are more than one, there is no answer. Then finding m and n, then going on to all the directions, then having a visitor, then having a priority queue, which is simply a min heap, then adding the first value. This is actually your time value. This is your row, this is your column, this is your row, this is your column, this is your actual time value on which you are actually doing your priority queue min heap, because you want to always get to a cell which is requiring minimum time. Then until your priority queue is empty, you find the current node, you get the current time, you get the current row, you get the current column. This is the current time I am at. I will check if I have reached the end. This is the corresponding current time I should return. And again, this, it will never be reaching here, but still we have written it here. If things are visited, continue. Again, you will say, why it is written here? I'll tell you why. Then, firstly, mark the current row as visited. Mark the current row as visited, because if I have reached here with this specific time, this is his corresponding minimum time. Then I'll go into all the four directions, find the corresponding next row, next column, check if it is a valid next row, next column, and also it should not be visited. If it is, then continue. If not, then find the flag value, which is the cycle type. Find the flag value, just making sure getting the difference. If it is even, then the flag value is 1, else the flag value is 0. Now, in that case, I will simply say that the time required will be the maximum of either t plus 1 or the grid next value plus the flag value, right? Maximum of these two will give me the time required to go on to that specific cell and the next row and next column. Now, again, this is a priority queue. Next time, whenever I want to get anything out from the priority queue, I will be getting the minimum time value from the priority queue out. Thus, ultimately, if I would be reaching the end, I will always be actually reaching up from the minimum time possible, because I'm always picking up the minimum time. Now, the fact that I've kept the visited here, even if it was here, is because if for any cell, again, consider any cell, for this specific cell I am at, let's say this is row comma column, current row comma current column. For its next cell, I pushed up this cell into my priority queue, and then I also pushed up this cell into my priority queue. Then again, this cell is picked up in the priority queue. This cell is also picked up in the priority queue with the corresponding t value, with the corresponding t value, with the corresponding t value. Now, let's say his t value would have been 2. His t value would have been 8 when it reached from here, right? But let's say it traversed, like obviously it is, yes, less, so it will be used first. Then I will go on to his neighbors. Let's say his neighbor was this one. Considering his t values, let's say 6. Obviously this is again less, so this will again say that for him his t value will be 7. So this same cell is pushed into a priority queue twice with a different t value. So it is always required that you check first, because next time in the next iteration, this specific cell with this specific t value, again this cell with this t value will be chosen. Next time again, the priority queue still has a t equal to 8 for the same cell. It should not be visited now. That is the reason I am making sure if it is visited, then continue. And only visit a cell when I reach onto it for the first time. Don't visit your cell here. Don't visit your cell here. It is just putting up, it's just simple DIjkstras. As do always put up the cell, try to see what is the minimum t value. Then when you encounter that minimum t value, it indicates okay, there was no other possible minimum t value, thus It is the minimum possibility value. Cool. Again, these small nitty-gritties actually make the code hard. That's it. Cool. I hope you guys got it. If yes, the time complexity is simply as you are using priority queue on every cell being ingested and got out from the priority queue. Every cell, which is n into m cells, it will be n into m, log m, n into m. It is more of a greedy. You can say it as DIjkstras also, but it is actually a greedy which we have leveraged and named it as DIjkstras. And the space will be O of m into n because you are using different arrays here, visited and entire priority queue itself. Cool. I hope you guys got it. See you. Bye bye. Take care. Do follow us on Twitter, and if you have not watched Community Post, do check it out. Bye bye.